So welcome to Lab 7 of EE100. We hope that you had a good long week break last week. This time around, we're gonna stick with the application area of biomedical signal processing. For example, the last lab that you had, we did some PPG signals, measuring of heart rates, measuring for oxygen levels, and now we're going to go even deeper. And so we're going to see Kiri, how electric signals or electricity, if you will, can be used to count cells, which are white blood cells in particular, on the order of micrometers, if I'm not wrong. So the point that we want to emphasize before we even begin this lab is that engineering is not strictly speaking about bridges anymore. It's not about building power plants. I've kept on saying this before as well. So it's not no longer just about electrical engineering in particular. एक power plant लगाने पे dam से आपको how do you transmit electricity, how do you distribute it. It's not about आपको सबसे पहले हमें कहा जाता है कि when we became electrical engineers कि घर की इस्त्री ठीक कर सकते हो नहीं कर सकते. So it's much more than just irons or electronics, or just some regular electronics, as we're going to see in this lab as well. One of the other points I want to mention here is that this lab, as well as all of the labs that we have seen before this, have an element of the research that our graduate students at the master's level or the PhD level, as well as our senior year students, have been involved with. Research that have actually helped them securing positions at top places across the world. Research that has been recognized by the international community. And it's once you're done with these labs, or when you're done with these tasks, it should really give you a sense of accomplishment, if you will, or sense of achievement, that what you've been able to achieve is a part, albeit a small part, of something which is much bigger, something which has been internationally recognized from our own work. Okay, and dare I say that that perhaps you should also have a sense of being privileged, in the sense that here you are, freshmen, and what the things that you're seeing, and the things that you've been able to accomplish, is part of something which is much bigger, right? So and the lab that we're going to do here is one of those, as our instructor is going to explain. So we have Dr. Numan with us, who is one of the co-instructors for this course. And he's going to tell you more about what the lab is going to be about. And maybe, Numan, if you can introduce yourself as well, tell the students about yourself, kahan se education hai, and so on, right? So, Numan, please.
Okay, Bismillah ar-Rahman ar-Rahim. Thank you, Dr. Momin. It's a pleasure to have opportunity to talk to freshman students. So before we talk about today's lab, brief intro for myself is that I have done my bachelor's from UT Lahore, and then I moved to for higher studies at Purdue. I did my PhD in 2008 in the area of semiconductor and nanoelectronics. After that, I had an experience working at chip manufacturing R&D at IBM for about 4 years. And then I joined LUMS in 2013. So at LUMS, I teach courses that mostly senior year students or graduate students mostly take. But previously, I have also taught junior year courses like semiconductor devices and electronics, microelectronics. For 500 level, I teach semiconductors, photovoltaics, and nanoelectronic devices. In research, I am looking at 2 or 3 broad areas which are quite different. Today's lab is more related to my work on uh, uh, biosensing. So we are basically trying to fabricate a novel or innovative biosensors that can be you'll see in this lab. And other areas that I'm working on are like on solar cells and solar technologies. But today's lab will be more on the biomedical side. So let me formally start today's presentation. So this is a blood cell counting. The specific device that we are talking today is called lab on a chip. As you will see why this name is being used here. So I think during the presentation, I would like if somebody has any question, to please feel free to ask, because I don't want to move very fast, or I don't want to uh, convey something which goes over the head. So please kindly, if you have any question, please interrupt me. Okay. All right. So I see one raised hand. So please, if you, Kasim, can you ask question?
So I wanted to ask you, said about the photovoltaic chip that cells that are used in solar panels. So what is the efficiency of those photovoltaic cells right now? Like, what is our progress?
Right. So solar cells, if you talk globally, solar cells have the commercial ones, which are widespread in the market, are the state of the art champion cells. They touch about 25-26% efficiency. But the common one which are available, that you, if you go to the market and you ask about the efficiency, you will probably see 16%, 17%. And there are different technologies also, like so that depends what kind of, are you talking about research cells, or you're talking about those which are available in the market. But yeah, so that's one thing which is probably not today's lectures focus, but we can talk about it if you want later on. So any
Thank you.
other? All right, so let's move on. So specifically, these devices that are called lab on a chip, they are basically meant uh, uh, to bring about a major change in how the medical lab tests are being conducted nowadays. So as you know, the medical tests are most essential part of the modern healthcare. Any serious problem, if you have anybody, if you goes to hospital or a physician, you will probably be asked to have multiple lab tests, including blood testing and many other kind of tests. So um, as you know that sugar level, electrolytes, they are all the blood tests, and some kidney functions, and many others which are needed for lot of a variety of diagnostic needs. And because of this pandemic, the people, common people have now this I think understanding that how critical is these lab tests for infectious diseases like COVID. And previously we have seen dengue and other things that are locally that have been prevalent. But COVID-19 is something which has everybody now talks about increasing the number of tests. So that we have Suktai Labs, Aga Khan, Shokat Khanam, they basically get samples from patients, and then uh, they get back to you in time, in days or hours. The way to go forward is to basically change this practice from centralized to locally personalized test kits that people can use, or people can have easy access wherever they are living. So in the next slide, we will elaborate something more on this. So currently we have a loose connection between patients and the tests and the physicians. If I go over the standard procedure that is being followed, that you go to if anybody has uh, has a need of a blood test, for example. So either you will go to one of the outlets of these labs, or if somebody is admitted to a local hospital, then the blood sample will be taken from the patient, and it will have to go to the um, a centralized facility, which is a sophisticated lab, and many high-end equipments are there, and trained technicians are present. They are doing all the testing that is needed, and then it goes back to where it is needed, to the patient or physician. Now let's look at some of the major problems that this standard practice has. So first of all, it has a long turnaround time. It is easily several hours, and it can take up to many days, depending upon the uh, nature of the test. And it's also not accessible to everybody. People who are living in remote villages or small towns, they may not have collection facilities very close by, or they may not have awareness also to how to conduct these tests. Also, the cost is a big factor. It's not affordable to everyone, especially to the poor people. And also, to establish a testing facility needs a very high capital cost. So at the end, it's not convenient. So we are looking for a big change in this practice. So what we will be discussing today is can everybody hear me?
Yes.
Oh, okay. So I was basically talking about some of these innovative and emerging things that are promising a revolution in this lab testing, or how people do the medical diagnostics. Some of these devices have actually recently commercialized. For example, Abbott has this device called iStat. It's a handheld blood analyzer. It can do the complete blood count, blood sugar, electrolytes, many other kind of routine tests that people need to do in their regular medical diagnostics. Um, for COVID-19, there are actually many companies have actually launched these point of care kind of devices, and Abbott has one of them is Abbott ID. It's a 5-minute rapid test for COVID-19. Initially, it was considered to be a big success, but later on, it kind of had some issues with the accuracy. But nevertheless, people are working on these things, and they are rapidly improving in the accuracy also. The Imperial College London has recently also launched a device for COVID-19. It's called DNA Nudge, and it's also a rapid test for COVID. Previously, Imperial College had a similar point of care device for influenza. Harvard is working in this area quite aggressively. They have this small chip which you can insert in your cell phone, and this chip actually has the blood sample, and the your cell phone has an auxiliary device which can read the signals, or it can sense whatever you want to do on the blood sample. Likewise, there is from John Hopkins University, they have developed this wearable sensor. It's a sweat sensor. There is a typo in the spelling here. So it's a wearable sweat sensor, it can it can detect many useful information just from the sweat that normal people have. I saw a hand raised, so if you have any question.
Yeah, sir, that's me,
Mhm,
Isra. Sir, I
mhm.
have a question. You previously mentioned the regular testings are quite expensive and not affordable for some people. But sir, these devices, what I think is obviously they would be also quite expensive, like the manufacturing cost and everything. So, agar we compare the regular testing with these testings, isn't these devices more expensive? These devices and testing, the procedure, everything is more expensive than the regular testing.
हाँ देखो इसमें ना two things are involved. One thing is the actual cost of the device, and the other thing is to repeatedly do the testing. For example, आपने अपने blood electrolytes test करने हैं. You purchase this device, and then this device kind of has a cartridge in it. So you have like a small piece of like a plastic where you will prick the your finger and give the sample to it, and that cartridge will be inserted in the device, and it will do the reading and give you the result. So the device it can be a little bit expensive, not because I think this one, which is this COVID-19 test, this DNA device, this probably is less than $100, and the one which is for influenza, it was, I think, around $20. So it's not very expensive. The So it depends upon actually the nature of the device. If you have something which has a test unit and a cartridge, so cartridges can be reused, and there will be a price of cartridge, and the handheld equipment which is used to test the cartridge has its price, but that price is one time price. And the cartridge will be not as expensive. The other thing is that it's basically like you it depends upon uh, the size of the production of these devices. So if these devices get um, if these devices are mass produced, if it's like computer chips, like the memory sticks that you buy from the market, to make those devices, it takes a huge investment. Like a semiconductor fab takes billions of dollars to establish. But since these memory sticks are produced in millions and millions, the actual cost of the product is very small. So once these devices are gets popular, and more people start buying these devices, the cost will rapidly go down. So even if currently you see the prices are not as lower, the the potential is that it can be lowered to quite a small value, right?
Okay, sir, I got it. Thank you.
Okay, so let me move on. So
Ask you a question.
sure, sure.
Sir, just like you were saying that this particular device, which is in the middle, it costs less than $100. So just like if we talk about decades and decades ago, we had a computer. We made a computer that had a size that was as large as a room, and now we have so small computers. We have reached a point that is like productive efficiency. At the same time, what is the purpose of like buying this when these pharma companies are like they're also going to purchase it at a very lower cost as compared to the very same devices with the very same function which they would have purchased probably a decade ago at millions of dollars. Now they have the same facility to purchase it at $100. So at the same time, the price of doing those particular tests is also going to come down. And what is the purpose of like buying them personal use?
Right. I think it's the comparison is basically like if you let's say if somebody has a diabetes, and he or she has to do the test every morning. So one way is that every morning the person will go to a facility, a lab facility, and do the give the sample and wait for the results till evening. The other the other opportunity that these handheld or portable devices are providing is basically you can do the test at your home instantly, very easy to use, no need for a trained technician to help you. And especially in the remote areas where the testing facilities are very limited, if people get access to these handheld portable things at a very low cost, then it can bring a big revolution in especially for the infectious diseases where we don't know how the pandemic is uh, uh, increasing, or from where it is where are the hotspots. So it's these kind of devices can bring a very big change.
Sir, I have one more supplementary question. Can I ask?
Sure.
Sir, if we look at this COVID-19, this particular device, and if someone like purchases it for like, let's say $100, he keeps that at home and like he's doing his test or he's doing the test of his family members, won't it be like difficult for the government and organizations or like looking after those hotspots, the word you use, hotspots, for like
Mhm.
seeing where that virus is like spreading up? So it will get it will be not getting this very same response as if someone is like infected. He's not going to tell the government or the authorities, just like
Mm.
thinking it is stigma in a society. So won't it be like negatively impacted if you like purchase it?
Yeah, so this is a very good question, and I think it all depends on how the public organization or government is basically using these kind of technologies. For example, if this device is widely available, let's say, and government conducts like random surveys to different localities where they suspect the people have problem. So it's very easy to conduct tests using these kind of very convenient devices as compared to the standard test that currently the COVID 19 test. As you know, the standard test is not very convenient, and it's not also instantly giving you the result. So if these devices are being used by government, uh, I think they can use them in a way that these could be quite helpful.
So, sir, technically, these devices also have an opportunity cost attached to them.
Um, I'm sorry, I did not get the question. Can you please repeat it?
So, sir, I was saying that like this technology has a very big opportunity cost attached to it too.
Yeah, so yeah, that's right. So I think uh, that's why these devices are being very widely researched. So if you go to any top university, you will find research groups which are working on these devices. And there's a big market potential also. So big companies like Abbott and other companies, they are spending huge money to basically develop such devices. Uh, Any other
Thank
question?
Sir, thank you.
Okay. So let me move forward. So the particular device that we are focusing is called Lab on a Chip. So Lab on a Chip is one of these portable or handheld point of care devices, but it can be thought of an ultimate point of care device because it has all the functionalities or desires that you could have in a in your portable device. So I'm just comparing here standard equipment which is used for the blood counting in today's labs. And this is a equipment you insert your bottles of blood in it, and it will do the analysis and give you uh, the results. So compare it with a very small chip, like a chip that you can find in your smartphone or a laptop. Like it's like a microprocessor chip. Its size is like a coin, and if you zoom this in, you will see that it is a kind of it has an electrical circuit printed on it, and that circuit has two, three main components that I will explain in the coming slide. So, so in terms of functionality and in terms of the size of the device, lab on a chip is the ultimate device that people are trying to make. And the word itself is saying that you are basically trying to implement a whole lab on a computer chip. So that's what lab on a chip means. So if we focus on the components that this biochip has, so you will see that there are three main things. One is uh, the microfluidic part. Microfluidic part means that there are channels of micrometer size, and inside those channels, your blood sample will flow. Microelectrodes are there to electrically sense whatever you want to sense in the blood sample, and the microelectronic part is a circuit that can have many subcomponents like amplifiers, filters, etc., that will process the signal and extract the useful information for the user. So yeah, so that's um, that these were the components, and now I will basically explain the basic principle of electrical sensing, specifically how you can electrically sense a biological cell. So this diagram is basically you have a blood sample, which is a diluted blood that you got from a patient. You put it on in a bigger container, which is on the outer side, and there is a smaller container also, which is immersed inside. Uh, so the round things are basically the blood cells. So these things are the blood cells that you want to count. So what you will do is that you will place a voltage source. One end will be in the inner container, and the other end will be in the outer container, and you will force these cells to pass through a very tiny aperture, which you can see here. So, there can be a flow pump which is sucking the blood from the inner container and uh, moving it backwards in the bigger container. So in that way, your blood cells will flow through that small aperture. And if you zoom into this aperture area, you will see that one by one the cell will be crossing. It will be crossing this aperture. Now what you do is you place a sensor, a voltage sensor across the inner container, and the inner container has basically two disjointed parts where which you can think as electrodes. They are like terminals which are connected to your voltage sensors. So across the aperture, you have two electrodes through which the cells are passing one by one. And what you expect is that as a cell crosses the aperture in between the two electrodes, there will be some voltage change during that time interval. And if the size of the cell is bigger, then the voltage pulse will also be bigger. So that's a basic principle how the cell information is converted into electrical information or a signal. So we will talk more and more about this in the coming slides. So what we want to do is basically one thing we can do is, since we have ability to count cells, we can do the complete blood counting, which is one of the very common tests that is needed for a lot of variety of diseases. And inside a CBC, you will see that people measure white blood cells, WBC, red blood cells, RBCs, platelets, um, and these things have a different size range. So WBC will be of the order of 10 micrometer, RBC maybe around 5 micrometer, and platelet around 1 micrometer. So you have the size variation with the type of the blood cells, and that size variation will be used in our device to basically give you this count of uh, different types of blood cells. I saw a hand raised, so please go ahead.
Said the difference between those two plates from which these molecules of white blood cell and red blood cells and these platelets pass. So is this like judged upon the difference in voltage, or it's like practically counting 1, 2, 3, 4?
No, it's actually, I will talk about this particular thing in coming slides, but basically we are uh, measuring the voltage change in between those two electrodes. So as the cell crosses, you will see this voltage change, and that will be the information that you get from this is that a single cell has crossed your aperture, and by counting all the cells that you have um, in your sample, you will be able to get a lot of pulses like this, and then you will count those pulses. So that's the part of the lecture that we have today. We have to discuss this in coming slides. Okay.
Okay, sir. Okay, sir. Thank you.
So precisely there are some questions that we will address today, and also in your tasks that you will be doing. We are we start with the basic question that how a biological cell responds to an applied signal. Then okay, the second question is that okay, we now if we have now understood the principle of the device, what is the practical way to make these devices? I will briefly explain that also. And the last part is to how to analyze the output signals from what we get from these devices. So that's also related to your lab task. So starting from the first question, that what is the electrical response that you expect from a biological cell? So you might have seen the physical picture of a, biological cell in your some of your biology courses, or previously in your high school or A levels. But a biological cell contains a lot of different subcellular things. The main components are this outer membrane that's called a cell membrane or a plasma membrane. Inside the membrane, there is a thick fluid which is called cytoplasm. And then inside the cytoplasm, you have nucleus and many other things. So fortunately, from the electrical point of view, all these details that is hidden in the cell is not needed. All you need to know is what is the electrical equivalent of this biological cell. So if we now try to understand what's the electrical equivalent of this biological cell, the first thing is that the cytoplasm, that can be thought of as a resistance. So like anything has has an electrical resistance, cell also has an electrical resistance. Additional thing that is present other than the resistance is something which is called a capacitor. So membrane, which is the outer shell, it acts like a capacitor. So there are two capacitors on each side of the resistor. And if you don't know about the capacitor, it's fine. But basically, capacitor is also an electrical component which is different as compared to a resistor. A resistor is just something which dissipates your power and doesn't do anything else. Capacitor has an additional ability to store the electrical charge. So, uh, but that detail is not needed for our discussion today. You can consider capacitor as something which will give you a resistance, but that resistance will be depending upon the applied signal frequency. So that's something which is uh, a detail which may not be needed for you to understand today's lab. So what we got from the cell is this simple electrical circuit which has two capacitors and two resistors. Cm is the membrane capacitor and cytoplasm resistor is inside. And if your cell is inside a blood, then there is also this additional external resistance Rs, which is due to the blood which is surrounding the cell. Now, uh, from this simple picture, we want to understand what happens if you have two electrodes and your cell is in between those two electrodes. Like in the previous slide, we saw that there is this aperture and cell is sitting inside, passing through that aperture. So now we want to connect these electrodes, let's say positive and negative. Um, and then we want to see that what will be the complete electrical picture of this device. So if you look at this, you will see that since the blood or any fluid, it has many ions like electrolytes that are maybe sodium ions, maybe potassium ions. So all these electrolytes inside the blood, they are charged particles. So they can be positive, they can be negative. So all these ions are inside the blood sample, and your let's say your white blood cell is also present. So what the complete picture will look something like this, that you have a cell in between, and all those ions which are positive and negative, they will be moving towards the respective polarity of the electrode. So we have a positive electrode here, we have a negative electrode here. So you will see that the ions are moving on the negative are moving on the left side, positive are moving on the right side. And because of this movement, you will see that the ions will make a layer on each side. So that layer also has a small electrical equivalent. It's also a combination of a resistance and a capacitor. So we have additional component that got attached to the cell circuit. So if we combine all these things, we will see that the complete picture looks something like this. And so from the biological cell, we just converted that thing into a simple electric circuit. Right? Um, so don't worry if you don't understand all the inner like intuition of the circuit, but it's just to give you a idea that a biological cell can be easily converted into something which is electrically easy to analyze. Now coming to the lab on a chip device, what kind of like structure that the device can have. So this picture is illustrating that structure. So you will have some inlets where uh, you will take a finger prick and send the blood sample through some inlet that is here. And there can be additional inlets where you can put some chemicals or reagents if you want for the for processing the for diluting the blood, for example. And you will flow the blood through these channels, which are the microfluidic channels. They have a size of roughly, let's say, 10 to 20 micrometer diameter of these channels, and the cells are flowing, and eventually they come to this area which is this yellow lines. So these are the metal electrodes, which are also micrometer scale. That's why you have this, you call it microelectrodes. So the cells are passing through the microelectrodes, and then they got on the outer side, which is the outlet. If you zoom this area, so this area is most important area to for the device, because that's where you are electrically sensing the cells. So if you zoom in this particular area, you will see that the picture is something like this, that this is like a 15 micrometer width, and the cell is also 10 to 15, let's say 10 micrometer uh, diameter. It's moving inside the channel in this direction, and these things which are uh, placed in the bottom, these are basically the electrodes. So this is the inner electrode, this is the right electrode, and here is the left electrode. So I will explain in the coming slides why do we have three electrodes and how do we actually sense the cell. But this is just a first introduction to how the cells are being sensed in the microfluidic channel. If you want to just do the WBC cells, what you can do is you can put some chemicals through the additional inlets, like these additional inlets, and there are some chemicals or reagents available that will destroy the RBCs, and all you will be left is this yellow things, which are the WBCs. So you can do selective counting also like this. So you destroy every other thing and let the WBCs cross through the electrodes. That's also possible. All right. So now come to how do we actually sense the cell? So cell is passing through, and these are the electrodes. These 1, 2, 3, these are electrodes, and cell is flowing from left to right. So an easy way to sense the cell is, you know, that you have to apply an input voltage, like um, in the original principle we saw that we have to apply an AC voltage. So that's where we are applying it to the middle electrode. So this is the input voltage, an AC signal that we are applying in the middle, and on the outer electrodes we are uh, sensing the impedance, which is between the electrodes. So here, so this is the left electrode. We are sensing the impedance, means that you it's like a resistance. So you are measuring resistance between the left electrode and right electrode here, and here you are measuring the resistance between electrode 2 and 3 on the right side. So the middle electrode is the input signal, and the outer electrodes are to sense the whether the cell is present or not. So electrically you can imagine that this thing we already talked about, that this is the electrical circuit of a cell, and since there is no cell here, you will only have this uh, solution or the blood resistor. So that's the electrical picture. Uh, how the things dynamically vary. So let's suppose that at a particular time instance t1, the cell is crossing between electrode 1 and 2, and we have electrical equivalent is drawn in the bottom. At a later time, which may be some milliseconds or microsecond later, the cell actually moved to between electrode 2 and 3. So if in this case, the electrical equivalent will be completely swapped. So your cell now is on the right side, and the blood, simple blood, is on the left side. In the original case at time t1, the cell was on the left side and your blood was on the right side. So if you now um, actually um look at the signal, that is uh, we will later on talk more about this output signal, but this is the output signal that we are getting. So V1 is the voltage at the left electrode, V2 is the voltage at the right electrode, and we are basically subtracting this voltage and plotting this delta. So delta is we are just subtracting the voltage at from that we get at the right side, and voltage that we got on the left side. So we get kind of a bipolar pulse. The pulse, the first, the when the cell is crossing between electrode 1 and 2, since we are doing this delta V2 minus V1, we will get a negative pulse. This negative pulse corresponds to this situation. And later on, when the cell has moved to the uh, right side, then the V2 minus V1 will be positive. So you get the positive pulse. So this is the signature. This whole thing is the signature that a cell has crossed your microelectrodes. So if you detect this thing on your output signal, you will say that I have got one cell. I have counted one cell. So that's how you, one by one, you will count all the cells in the sample. So again, the if the size of the cell is smaller, then the magnitude or the amplitude of the output signal will also be smaller. So that's how you will get a distribution of cells. Like you will distinguish between red blood cell and the white blood cell, or if even if you have only one kind of cells like WBC, even then you can see that what is the size distribution of that particular kind of cell. Okay, so one question, I have seen one hand, so please go ahead.
So, for the case of RBCs, red blood cells, if like this graph is moving on, we have to see that the number of wavelengths of these graphs is going to be equivalent to the number of the particles or the red blood cells.
Right. So this thing, this bipolar thing, this thing is a signature of a cell. You can see this. This is a very unique thing. Otherwise, the signal is moving like this. So if the signal is moving like this, we said that this is the background. This is not the cell. But as soon as you see this bipolar thing, you know that the cell has crossed. So that's the this signature or this pulse is basically uh, how you sense one particular cell.
So in the case that we have, let's say, let's assume 2 or 3 RBCs, there will be 3 sigma diagrams like these.
Right, right. So I will show you what we actually get in the uh, um, in the output. So we have actual measured signal from our device. So I will show you just few slides down. All right. So, so as I said that I will also tell you how we make these devices. So an analysis is very interesting and very exciting, but if you don't have a device that you can use, then everything you cannot do anything. So we actually start with making these devices. We fully fabricate these devices at LUMS. So like these pictures are just some of the um, uh, microfluidic channels and electrodes that we have recently made. So these are the microelectrodes, and these are all microfluidic channels. So what you do is that you make the electrodes on glass plate, and you make your microfluidic channels using a soft polymer, and then you bond these two things together, and that's how you basically uh, you make a contact between these microelectrodes and the microfluidic channel. So I will tell you some basic like procedure how we do that. Maybe I'll show you this video first. So this is from device that we fabricated, and then we uh, made this video when the cells are flowing through this device. So let me show you. This is like a 1 minute or lesser. So these small dots that you can see, if you look very closely, you will see these small dots, like the dots that you can see. These are all cells. So these cells are moving, and this, and here we have electrodes. So electrodes are not visible in this video, but actually you have electrodes. So one by one, the cells are moving through the microelectrodes, and and on these microelectrodes, so we are measuring V1, we are measuring V2, and we are putting the input voltage here. So, so that's the way that we do this. Okay, so let me move on. Um, all right, so I'll briefly explain how we actually fabricate these devices. So we start with something which is called wafer. You know that silicon is the primary semiconductor which is used in all the microelectronic devices, everything, microprocessors, your USB chips, everything is made on silicon. So we also start with silicon, but we use silicon just to facilitate the fabrication process. Eventually, the thing that we will make will not be on silicon. So we start with a silicon wafer, we put something which is called a photoresist material. So this red thing is a photoresist material. We put it on the silicon wafer, and then we spin the wafer using something which is called a spin coater. So we spin coater will it will revolve this at high RPM. So then this photoresist will be evenly spread on throughout the wafer. So basically we are preparing our something to basically make those microfluidic patterns. So this uh, third picture is actually explaining the process of photolithography. Photolithography is simply what uh, we have something which is called a photomask. So photomask has your desired feature. So this thing is your desired feature is already printed on the photomask, and your silicon wafer which has the photoresist is down, and you shine a UV lamp from the top. So what will happen is that UV light will only pass through the desired patterns, because the rest of the area is black. UV light will cross this transparent thing, which is your feature, and the UV light will be actually be transferred on the photoresist. Now this photoresist has a property that it reacts with UV light. So since it reacts with UV light, then only this part of the photoresist which got the exposure had a property which is different from the other parts of the photoresist. Now what will do is that we will put silicon wafer that has this pattern into some chemical, and the chemical will etch out everything except for the part which got the UV exposure. So that's called a master mold. A master mold is something which can be used to make multiple devices. So once we have the master mold, what we'll do is that we will put um, uh, this liquid, which is actually it will solidify to after some time getting some heat. This liquid will solidify, and all that the patterns on the master mold are now transferred on this soft polymer, and eventually you got this final thing which is also called a microfluidic stamp, and it contains all the channels that you wanted to print on the device. So this is roughly what we do. And similar procedure is done to print the micro electrodes, the metal electrodes. And then we bond them together and make the full device. Some equipment that we use, as I said, we do the photolithography. So we have this equipment to do the UV exposure. We have the spin coater. When we put the photoresist, then it move at a high RPM and to evenly spread the photoresist. We have a thin film deposition. That one is used to make microelectrodes. So microelectrodes, I did not get time to explain how to make microelectrodes, but this thin film deposition is you put very thin layer of metal and you do the photolithography to make the patterns on that thin layer. We need a clean room, and we have sort of a clean room, very small one available at LUMS. Then we test the device under microscope and we connect it with our laptop or external devices to take the data. Okay, so once we have the device ready, then it's time to look at the to test the device and look at the output. This is one of the outputs from the device, and this is like 2 minutes signal. In the lab that you will do later after the lecture, you will get chance to play with this data. So it's showing that there are a lot of pulses, and each of these pulses corresponds to one cell that you detected. So if I zoom at one particular pulse, I will again see that bipolar thing that I explained a few slides before. So, okay, so we have to actually do the counting. So visually we can see, and we see that there are a lot of cells. How to count those cells is the next question. One way is to count those cells is first to draw a histogram. Histogram is basically is nothing but is a way to look at the data distribution. uh, I will take a few minutes to tell you what is basically a histogram is. So I will use a very simple example. Let's say that we have about 20 persons, um, and they have different ages starting from 20s and going to 90s. We want to see that in each category, uh, if we want to categorize the data in various bins, how many peoples are present in each category or each bin. For example, I can say that I want to look at 10 years bins and see how many people are there in each bin. So in 20s I have 2 people, in 30s I have 4 people, and likewise. And I can plot this, and this thing is called histogram plot. So the y-axis is basically showing the frequency of each bin. So in 20s I have 2 people, in 30s and 40s I have 4 people, in 50s I have 5 people, and so on. And you can also choose a different bin size. Like if I choose 20 years bin size, then I will have a different uh, kind of a distribution. But the thing is that if you have plenty of data, then the bin size is kind of less important. It's important, but it's not too much affecting the shape of the distribution. And in MATLAB, when you do this histogram function, it can automatically choose the bin size according to what the data you have. So going back to what we get from our data, so if we plot the histogram of our data, so what we see is basically these are the frequencies. I have written count here. It's same thing, like we have all these pulses, and the pulses have different amplitudes. So what we are doing is basically we are making small bins in the voltage axis. So this is the voltage axis, and we are making small bins in the voltage axis, and in each bin I am plotting how many pulses I got in each bin. So this is the basic basic idea. Now this picture looks very strange. This is like clearly we have two different kind of distributions. One distribution is like tightly squeezed, this one, and the other is kind of broad one. So what this is corresponding, uh, two different widths and clearly two different distributions. Now, I can tell you that the tighter distribution is because of the background signal, and the wider thing is due to the actual cell peaks that you see in the data. And if you go back to the original picture, you can kind of get the um, idea. If you if you see the original time series, you get the idea that sorry, here. So you get the idea that the signal is actually has a bigger amplitude and the background has a smaller amplitude. So that's the histogram is also telling you the same thing, like the signal is actually wider distribution. So that's what you have. And in the handout, you will see you will use MATLAB histogram command to plot this histogram, and then you will look at this peak at this width, and you will calculate this width, and whatever will be this width, you will use this information to basically cross out this part of the distribution, because this is not needed. uh, the middle part, which is the tighter part, is the background noise. We don't need it. Actually, we want to get rid of it from the when we are counting the cells. So we will get rid of this, and we will focus on the peaks which are larger ones. So one other thing before I explain the lab task to you is this frequency domain view of the time series signal that we just saw. If you do the fast Fourier transform, the time series signal will look like this in the frequency domain. The frequency domain is especially helpful to locate the some particular noise peaks in the data. For example, this 50 hertz signal, it has a very sharp peak. So this is a noise which is commonly seen in the electrical circuits. If somebody in the students have any idea that from where this 50 hertz noise could come, go ahead and if anybody can any guess about this particular frequency. Have you heard about um, have you heard about 50 hertz noise?
सर ये यूजुअली रिफ्रेश रेट्स नहीं होते
दोबारा बताओ।
सर रिफ्रेश रेट नहीं होते यूजुअली ये किसी भी डिवाइस के
नहीं नहीं, ये एक्चुअली ये 50 हर्ट्ज बेसिकली आपके जो घर में या कहीं पे भी पूरे पाकिस्तान में जो आपकी सप्लाई आ रही है वापडा से, वो 50 हर्ट्ज पे आ रही है। जो आपके 220 वोल्ट्स आते हैं आपके पावर आउटलेट्स में, उनकी नॉइज उनकी फ्रीक्वेंसी 50 हर्ट्ज है। तो जब आप अपने इंस्ट्रूमेंट्स को यूज़ करते हो जो आपने सेंसिंग पे लगाए हुए हैं, तो उनके अंदर ये जो पावर सप्लाई की नॉइज़ है, ये उसके अंदर आ जाती है, और यू गेट दिस पर्टिकुलर 50 हर्ट्ज नॉइज़। तो आपके लैब टास्क में एक काम ये है कि आपने इसको अपने डाटा में से निकालना है। तो दैट्स वन थिंग दैट यू विल डू इन टुडेज। और आप ये देख सकते हो कि ये जो बैकग्राउंड सिग्नल आपको नज़र आ रहा है ना, ये तो आपका एक्चुअल सेल सिग्नल है ना, बाइपोलर। लेकिन ये जो उससे पीछे चल रहा है, ये आपका बैकग्राउंड सिग्नल है। अगर आप गौर से देखो अपने बैकग्राउंड सिग्नल को, तो इसका टाइम पीरियड तकरीबन 20 मिली सेकेंड है, जो कि एग्जैक्टली 50 हर्ट्स को मैच करता है। तो ठीक है, तो यहाँ तक इफ एनीबडी हैज़ एनी क्वेश्चन, अब हमारा लेक्चर का कंटेंट्स पूरे हो गए हैं। अब मैं आपको लैब टास्क बताने की तरफ जा रहा हूँ। सो बिफोर आई गो टू एक्सप्लेन योर लैब टास्क, इफ यू हैव एनी क्वेश्चन about the lecture contents, please go ahead and ask. All right, so ठीक है, 2 पार्टिसिपेंट्स के हैंड मैंने देखे हैं, तो वन बाय वन आप पूछ सकते हैं। 3 पार्टिसिपेंट्स के मोहम्मद कासिम, आप पूछ लें। जी कासिम, आप क्वेश्चन पूछें।
सॉरी सर।
अच्छा, फिर मैंने आयशा का देखा है हाथ। आयशा, यू गो अहेड।
Sir, can you please explain the Fourier transform against frequency graph again?
हाँ हाँ बिल्कुल। ये जो फोरियर ट्रांसफॉर्म वर्सेस फ्रीक्वेंसी प्लॉट है ना, इसका हमारा जो प्राइमरी पर्पस है इसको ड्रॉ करने का, वो ये है कि हम देखना चाहते हैं कि हमारे सिग्नल में कोई अनवांटेड नॉइज़ तो नहीं है जो कि हमें यानी हमारे सिग्नल को इम्पेक्ट कर रही हो। तो अदरवाइज़ जो हमारा टाइम सीरीज़ वाला प्लॉट था ना, वो प्राइमरी हमारा प्लॉट है जिसकी बेसिस पे हमने सेल काउंट करने हैं। तो फोरियर ट्रांसफॉर्म लेने का पर्पस ये है कि हमें नज़र आ जाए कि इफ़ देयर इज़ एनी पर्टिकुलर नॉइज़ कंपोनेंट विच इज़ इन एम्बेडेड इन आवर टाइम सीरीज़ डाटा, जो हमें टाइम सीरीज़ में नज़र नहीं आ रहा लेकिन एफएफटी में इजीली नज़र आ जाएगा। तो इसलिए हमने एफएफटी ड्रॉ किया और हमें वाकई क्लियरली नज़र आ रहा है कि 50 हर्ट्ज़ पे एक बड़ा कंपोनेंट है नॉइज़ का। उसको हमने फिर अपने लैब हम अपने फर्दर एनालिसिस में इसको रिमूव कर सकते हैं। फ्रीक्वेंसी डोमेन में रिमूव करके वापस हम उसको सिग्नल को टाइम डोमेन में कन्वर्ट कर सकते हैं, जैसे कि आपने पहले किसी लैब में शायद किया भी हुआ।
So,
But there are so many other peaks as well, either nature.
yeah,
The
Aisha,
one you can.
so let me clarify here. One of the ways this may look different than what we've done before is that the scale on the x-axis that you see is a log scale, and the scale on the y-axis that you see is also a log scale. Okay, so this is earlier when we were plotting the Fourier transforms, they were linear scale on the x-axis and linear scale on the y-axis. Right now, what are the other peaks represent? There's a lot more to it. I think perhaps it's better that we don't go into a lot of those details in this lecture here, but perhaps in Padme, when the lab is over, you're more than welcome to stay back and discuss.
Okay, thank you, sir.
ठीक है, और किसी बच्चे का और क्वेश्चन? एक और हाथ मैंने देखा है।
Yes, sir. My question is regarding the fabrication process for these devices. Like, what sort of instruments, like tools, do we use to actually build these? Like, इतने
हाँ
because इनका like firstly diameter कितना होता है? Like जो electrode के जो pathways थे, उनका like diameter कितना होता है? And then secondly, इनको मतलब इतनी accuracy से कैसे बनाया जा सकता है?
ठीक है, लेट मी गो टू द मैं आपको उस स्लाइड पे ले जाता हूँ जहाँ पे हम डिस्कस कर रहे थे। आप क्वेश्चन सबसे पहले आप ये पूछ रहे हो ना कि कौन सा इक्विपमेंट ये हमें बना के दे सकता है, और सेकेंडली इनका साइज़ क्या होता है। तो इनका जो साइज़ है, अगर आप ये वीडियो वाली स्लाइड को गौर से देखो ना, तो जो स्मॉलर रीजन आपको नैरो रीजन नज़र आ रहा है, उसका साइज़ 15 माइक्रोमीटर है, और जो बड़ा रीजन है पीछे वो 100 माइक्रोमीटर के अराउंड है। तो जो पार्ट आपका सबसे ज़्यादा इम्पोर्टेंट है, वो पार्ट आपका तकरीबन 15 माइक्रोमीटर है, और हमने उसको पर्पसली 15 माइक्रोमीटर इसलिए रखा है ताकि वो एक वक्त में एक सेल को ही अलाउ करे, वरना अगर हम उसको बड़ा कर देंगे तो मल्टीपल सेल क्रॉस करेंगे और फिर हमें सेंसिंग में उसकी एनालिसिस में मुश्किल हो जाएगी। तो दैट्स व्हाई वी कीप इट क्लोजर टू द साइज ऑफ द सेल। अब उसको बनाना कैसे है और हाउ डू वी मेक श्योर कि कैसे ये प्रिसाइसली डायमेंशंस बन जाएं, तो ये इट्स ऑल द these equipments, ये जो आपको नज़र आ रहे हैं, जो फोटोलिथोग्राफी का इक्विपमेंट नज़र आ रहा है आपको, या जो आपको स्पिन कोटिंग वगैरह नज़र आ रही है, प्राइमरली जो फोटोलिथोग्राफी है, ये वो टूल है जिससे आप अपने कंप्यूटर की चिप्स बनाते हो। तो आपको पता है कि आपके जो कंप्यूटर की चिप है, जो आपके सेल फोन में या लैपटॉप में आपकी एक माइक्रो प्रोसेसर की चिप है, उसमें
Yes, sir.
1 बिलियन के करीब ट्रांजिस्टर्स हैं। तो अब 1 बिलियन के करीब ट्रांजिस्टर्स हैं और 1 सेंटीमीटर के साइज के अंदर, तो हाउ कैन यू मेक दिस थिंग? सो दिस इज वन ऑफ द वंडर्स ऑफ टेक्नोलॉजी, सेमीकंडक्टर टेक्नोलॉजी ने ओवर 40-50 years, ये जो रेवोल्यूशन आया है आपके पास कंप्यूटर्स का, दिस पार्ट ऑफ इट इज दैट पीपल हैव innovated these equipments and techniques जो कि आपको ये बना के दे सकें। तो फॉर्चुनेटली हमारे पास लम्स के अंदर ये इस तरह के इक्विपमेंट्स हैं जिसको यूज़ करके हम इतना प्रिसाइसली इसको बना सकते हैं।
Thank you, sir. That answers my question.
ठीक है, और एनी अदर क्वेश्चन? चलिए ठीक है, तो लेट मी क्विकली एक्सप्लेन द लैब टास्क ताकि आप आराम से स्टार्ट कर सकें अपना काम। तो बेसिकली लैब इज़ आपके पास एक ही टास्क है, उसके सब टास्क हैं फिर। तो यू हैव दिस 50 पॉइंट्स इन टास्क 1। आपने एक डाटा फाइल, यू हैव टू डाउनलोड दिस डाटा फाइल wbc.mat। ऑलरेडी इट्स अपलोडेड ऑन LMS। आप इसको अपनी मैटलैब की करंट डायरेक्टरी में लोड करेंगे एंड देन यू विल सी के इसके अंदर 2 वेरिएबल्स नजर आएंगे। वन इज द आउटपुट वोल्टेज सिग्नल, जो अभी आपको दिखाया था ना सिग्नल, द सेम सिग्नल यू विल, उसका डाटा आपके पास आएगा। और सैम्पलिंग फ्रीक्वेंसी आपको बताई हुई है कि किस इसकी सैम्पलिंग फ्रीक्वेंसी क्या है। आप उसको मैटलैब में स्क्रिप्ट के जरिए से लोड करेंगे एंड देन यू विल डू दिस फॉलोइंग टास्क। नंबर ए, यू विल प्लॉट द वोल्टेज सिग्नल वर्सेस टाइम, जैसे कि मैंने आपको भी शुरू स्लाइड में दिखाया। और आपको नज़र आएगा कि जो प्रोनाउंस्ड पीक्स हैं, जो बड़ी पीक्स हैं, वो आपके WBC सेल्स की हैं। हमने सिर्फ WBC सेल्स यूज़ की हैं, सो वी हैव द पीक्स corresponding to them. You can zoom them, you should zoom them and see कि जो मैंने आपको बाइपोलर टाइप की पल्स दिखाई थी, आपको भी वो नज़र आती है या नहीं। And then you will, in the next task, you will subtract the DC offset. And in the part C, after you do this subtraction जो आपने DC की करनी है, तब आप हिस्टोग्राम की कमांड यूज़ करेंगे, जो अभी हमने आज उसको थोड़ा बहुत डिस्कस भी किया है। और आपको इस हिस्टोग्राम की कमांड के अंदर जो आपका ये जो वोल्टेज V का वेरिएबल आप उसको देंगे, तो यू विल एग्जैक्टली सी दैट वो जो हमें 2 ओवरलैपिंग डिस्ट्रीब्यूशंस नज़र आ रही थी, यू विल सी देम। और फिर आप उनकी विड्थ्स को कैलकुलेट करेंगे बाय मैन्युअली ऑब्जर्विंग इट ऑन योर मैटलैब फिगर। फिर आप नेक्स्ट टास्क के अंदर, जो टास्क डी है, आप यू हैव टू काउंट द सेल्स। तो फिर आप फाइंड पीक्स एक फंक्शन है मैटलैब में, आपने शायद लैब 6 में भी यूज़ किया उसको। तो दिस इज़ अ वेरी हेल्पफुल फंक्शन टू, it will give you the count of all the peaks. But the catch here is that you have two kind of distributions. एक तो आपकी desired distribution है जो कि cells की वजह से है, उसके बड़ी peaks आ रही हैं। एक background signal की भी peaks हैं छोटी। तो you don't have to count the peaks in the background signal. अगर आप करोगे तो आपका आंसर गलत आ जाएगा, because background is not corresponding to the cell. तो आपके लिए लाजमी है कि जो बैकग्राउंड की पीक्स हैं आप उनको काउंट ना करें। तो उसके लिए फिर हमें एक एडिशनल एट्रीब्यूट यूज़ करना पड़ेगा फाइंड पीक्स में, जिसको मिनिमम पीक प्रोमिनेंस कहते हैं। और ये बेसिकली जो एट्रीब्यूट है, ये आप इसमें स्पेसिफाई कर सकते हो कि जो मेरी पीक है उसका एम्पलीट्यूड नेबरिंग पीक्स के मुकाबले में कितना ज़्यादा है। तो हमारे डाटा में इसी तरह ही है कि जो नेबरिंग पीक्स हैं वो बैकग्राउंड की हैं, वो छोटी हैं, और हमारा जो डाटा है उसकी पीक्स जो हैं वो बड़ी हैं। तो आप एक एम्पलीट्यूड स्पेसिफाई करोगे और उसको बताओगे कि इससे छोटी अगर पीक्स हों तो यू डोंट हैव टू काउंट दैट। तो वो आप फिर ये जो नीचे मैंने लिखा हुआ है ना फंक्शन, उसके अंदर आप यहाँ पे स्पेसिफाइड वैल्यू पुट करोगे। अब ये स्पेसिफाइड वैल्यू कहाँ से आएगी? ये एग्जैक्टली वही वैल्यू होगी जो आपने जो डिस्ट्रीब्यूशन हिस्टोग्राम में देखी थी ना, उसमें जो टाइटर डिस्ट्रीब्यूशन है ना उसकी विड्थ, दैट विड्थ इज कॉरेस्पॉन्डिंग टू द बैकग्राउंड। आपने उसको अवॉइड करना है। तो जो आपकी मिनिमम पीक प्रोमिनेंस है ना वो आपकी उतनी ही होगी जितनी आपकी वो जो टाइटर डिस्ट्रीब्यूशन है उसकी विड्थ है। तो दैट यू कैन स्पेसिफाई। तो अब मुझे कुछ क्वेश्चन नजर आ रहे हैं, हैंड्स रेज, प्लीज आस्क द क्वेश्चन।
Sir, can you please go back to the previous slide?
हाँ जी।
In this part B, when we are subtracting the offset value from the signal, wouldn't that eliminate the peaks that you are telling us to ignore in part D?
नहीं नहीं, ऐसा नहीं है। अगर आप सिग्नल को देखो ना, ये सिग्नल मैंने आपके सामने दोबारा खोला है। इसका जो मीन है, इसकी जो एवरेज है, वो उसका डीसी पार्ट है, वो आपको नज़र आ रहा है कुछ 0.0 समथिंग। तो यू विल सब्ट्रैक्ट दैट पार्ट एंड द सिग्नल विल शिफ्ट डाउन। इसकी कोई पीक ख़त्म नहीं होगी, ये सिग्नल एग्जैक्टली इसी तरह का ही रहेगा, बट ये नीचे की तरफ शिफ्ट हो जाएगा। ठीक है, क्योंकि
Oh, okay.
आपने कांस्टेंट से सब्ट्रैक्ट करना है ना।
Okay. So फिर वो peaks, I thought that those peaks were occurring because of ये offset value, but why are those peaks occurring?
ओ, जो छोटी छोटी वाली पीक्स हैं,
Yeah, the background noise that
हाँ
you're calling.
हाँ, वो आपकी हमने आइडेंटिफाई किया है ना, उसको एफएफटी के अंदर हमने वो बैकग्राउंड के नॉइज को आइडेंटिफाई किया। तो हमें नज़र आ रहा है कि 50 हर्ट्ज की जो नॉइज है वो एक बड़ा पार्ट है आपकी नॉइज, जो आपके बैकग्राउंड सिग्नल है उसका। तो ये आपका जो है वो आपका आंसर यहाँ पे ही छुपा हुआ है कि दिस इज बेसिकली जो आपकी
So
जो
the
नॉइज
50 hertz, the noise is not the same as the DC.
नहीं नहीं, हाँ, डीसी ऑफसेट जो है ना वो और चीज़ है, और उस डीसी ऑफसेट के ऊपर एक नॉइज ओवरराइड हो रही है, वो आपकी बैकग्राउंड नॉइज है, और उसके ऊपर फिर आपके पास आपका डिजायर्ड सिग्नल है। तो जो डीसी ऑफसेट है वो आपके इक्विपमेंट की बायस, आप जब उसकी मेजरमेंट्स करते हो ना, सेंस करते हो आप अपने सिग्नल को, तो आपके सेंस साइड के ऊपर कोई एक डीसी वैल्यू होती है जिसकी वजह से सिग्नल जो है वो फिर जो आपका एसी सिग्नल है वो उसके ऊपर ओवरराइड कर रहा होता है, तो उसको आपने रिमूव करना।
Okay, okay, thank you.
अदर क्वेश्चन? ओके, तो हमने फिर पार्ट डी को भी डिस्कस कर लिया। पार्ट ई जो है वो हमारा लास्ट पार्ट है इस टास्क के अंदर। इसमें आपने 50 हर्ट्ज की नॉइज़ को रिमूव करना है, और आपने अपने जो आप पीछे जो आपका टाइम सीरीज सिग्नल आपने प्लॉट किया हुआ है, उसको आपने फोरियर ट्रांसफॉर्म लेके उसके अंदर देखना है कि वाकई आपको 50 हर्ट्ज पे नॉइज़ नज़र आ रही है, एंड देन यू यूज़ द फ्रीक्वेंसी डोमेन फिल्टरिंग कॉन्सेप्ट जो आप पिछली लैब्स में यूज़ कर चुके हैं। आप उसको फिल्टरिंग करेंगे, एंड देन यू कन्वर्ट बैक इन द टाइम डोमेन बाय यूजिंग इनवर्स फोरियर ट्रांसफॉर्म। और फिर आपको नज़र आएगा कि वाकई जो जब आपने 50 हर्ट्ज नॉइज़ रिमूव कर दी है तो आपके जो बैकग्राउंड का एम्पलीट्यूड है वो छोटा हो गया। यू विल वेरीफाई दिस। ठीक है, और इन लैब टास्क के साथ कुछ शॉर्ट क्वेश्चंस हैं जो आज के लेक्चर से ही 2-3 क्वेश्चंस हैं, वो यू आल्सो यू शुड एड्रेस आल्सो दैट। तो आई थिंक अगर हमारे और कोई क्वेश्चन है तो आप पूछें, अदरवाइज वी कैन प्रोसीड टू द लैब।
Right. So before we begin the lab, may I take the floor and just let you know that we're going to try something new this lab, which is there's only one task for the lab, and that task is not mandatory. Okay. So the task that you see on your screens is actually a bonus task, right? So, and we want to just take the pressure out of meeting a deadline for submitting just for the sake of submitting it, but rather we want to move towards a place where you do it out of fun, without that pressure, and in the process learn something new. Okay. So this, once again, let me repeat it again. This is not a regular task. If you do not wish to do it, that's your choice, right? If you do wish to do it, so that will be counted as a bonus task worth 50 points, which you can use to replace tasks earlier in the early labs, or the labs that are going to come. There are only two left. Okay. So with that note, so let's break up. If you have questions, you can stay here in the main meeting room. Questions about the task or about general about some research that Dr. Numan is conducting with the students, or anything else. So you're more than welcome to stay here. Otherwise, you're free to start the lab or do something else if you don't wish to do this bonus task. Yes, Jazral, there are no mandatory tasks this week. Right? And if you go through the handout, I mean, we list a bunch of reasons why you would want to do a bonus task. You would want to do a bonus task के बाद में आपका workload कम हो जाए. You would want to do a bonus task because you want to make up for something that you missed in the earlier one. But what we would like and we hope is that some of you and most of you would do it just for the sake of doing it, for learning something new, right? And that itself is a bonus. And yes, Isha, there will be a deadline. If you want to make that deadline, you want to replace a regular task with this bonus task, the deadline is next Friday. Okay. G. Irtaza, please go ahead.
I wanted to ask if how do we essentially find out how our labs were graded? Do we like go to TA and ask them how we got graded in?
Yes. So if you have concerns about the grades that you got in the last labs, so you can approach the TAs, and they will help you. Okay. So lab
okay.
6 grades have
Also,
not been
is there a
uploaded yet.
deadline for the bonus task for the previous labs?
Yes, of course. The bonus task
Yeah,
deadline.
I got that. I just wanted to ask another question.
Yeah. Ji, go ahead.
Oh, okay.
So Itza, do you want to speak up? And for the questions in the chat box, no, the lab 6 has not been graded yet. It will be over the weekend. So you will be able to see your grades for lab 6 over the weekend, inshallah.
I just wanted to ask if there was a deadline for the previous labs bonus tasks because I wanted to do them, but essentially because of quizzes and midterm prep, I wasn't able to do them. So I was wondering if I could submit them later and still sort of get credit, or just maybe do them for fun. That's fine with me as well.
So if you want to do them for fun, by all means, you're more than welcome to do it. We'd be very, very happy if you were doing it just for the sake of fun. Lekin unfortunately, there's a policy here in place. So the deadline for the bonus task is exactly the same deadline as for the regular tasks.
Oh, okay. Okay, brilliant. Thank you so much.
Yes, Umair, Ramzan, we will be returning to normal assignment questions from next week. Yes, it looks like you foreign karna chahte hain normal assignments, so we'll be more than happy to comply. ठीक है, Umar? And the other thing is, I mean, you should have the courage to unmute yourself, show me your face, right, and speak up. I mean, it would be nice to see your faces and instead of just black screens. I mean, people complain about online teaching, online instruction, but then for some reason they're not willing to engage. Right. Thank you, Samina. Excellent. So I see some volunteers at least, and it's very happy, very happy to see at least.
We did plan once to turn our cameras on for you, but then we had a surprise lecture and we couldn't do that.
Challenge. At least I see your faces now. Everybody sees your faces. Fourth one. Thank you, Mera. Thank you, Basit. Thank you, Abdullah. So we hope to see you soon on campus whenever situations allow. With that disclaimer. So, मैं आपको I don't want to. मैं record तो नहीं हो रहा. I record. Sorry.